Hey guys, welcome to another episode of Building Tensorflow. Today we're going to be building the the dot product multiplication, the matrix multiplication on the GPU. So the result is actually going to look the same, but so we have in our main file we have these tensors m1 and m2, and then we can just print out their value, and then we do the dot product, and then we run this. So if I just run make GPU, so I've already coded the GPU part. I'm going to just step through the code and tell you how to do this. So how did we do this? So effectively, mm, we go into our matrix.h. Our matrix.h has a boolean called GPU true or false. If it's false, it should still work, right? That's on the CPU. This is on the GPU. So I'll show you what's happening here. And so if GPU, let's see, so we're in we've already done this. We have a matmul, and then in the matmul calls matmul util when both these matrices are of the same size, which is 2D matrices. When both the LHS and the RHS are 2D matrices, the matmul util runs. So when this runs, the code just sees if the GPU is on or it's accessible. You run this, else you go through the simple CPU version of the code, which we saw in the last episode. So this is just doing the normal on to the power 3 complexity, three loops, and this is your normal matrix multiplication. So we know this code is right. Now what we need to do is we need to do the same thing on the GPU. So GPUs have a lot of parallel cores. So the way things are faster on the GPU, especially operations like matrix multiplications, are that it runs a separate computation that is independent of the rest of the other computations on a separate core. So you can essentially parallelize all your operations. So for example, you see that for these two loops, so this iterates over the rows, the first row, and then so this goes to so what this code is doing here is it's finding out the exact grid on the matrix that is going to be created out of the dot product, and it is selecting that grid and then updating the value here, which is the sum. So this is sum value. So to calculate this sum value, we use another loop that iterates through the column of the first matrix and the row of the second matrix, and then we simply do do a convolution operation, which is just multiply and add them all together. So as you can see, this is the right hand side and this is the left hand side, and it just multiplies and just adds. So this is our code line. So what we can do here in the matrix multiplication, we what we can see here is that when you calculate the sum, that is not independent of everything else. So to calculate the sum, you need to iterate over like the column of the first matrix and the row of the second matrix, but you don't, the rest of the grids of the matrix that is going to be formed do not need to wait for every other grid to finish their operation. They can do this parallelly. So we can actually parallelize these two loops. We can run these two loops on separate cores, and and just do the computation of this loop on our core, and then we just update the sum to the position that the core represents in the resultant matrix. And so you're effectively writing to data. You don't have any conflicts in the writing. and reading, obviously it has no conflict, so we don't have a read write conflict at all in this situation. So let's step into the dot GPU function. uh, so what this does, it takes a matrix, which is our resultant matrix. This is our left hand side, this is the matrix on the left, and this is the matrix on the right, and this is called start and start res. So start and start res, as you saw in the previous episode, the start denotes the start of the left hand side matrix, and start res denotes the start of the resultant matrix. And basically RHS is starts from 0 because it's already a 2D matrix, and this could be like a 3D or a 4D matrix. Okay, so so this code is the same as the previous function, the CPU function. And then what we need to do is, so the GPU is separate from the CPU, so we need to copy our CPU vector, our vectors on the CPU to a data structure on the GPU, so that the GPU can run it on its cores and share that memory among all the other cores. So what these two lines are doing are just they effectively, these are just taking out the pointers of our vectors or our CPU vectors, and then this is also taking the pointer of our resultant CPU vector. Then it's creating these 3 new pointers, and then we run something called CUDA malloc, which acts like malloc but on the GPU. So it allocates memory on the GPU, and we allocate the same size as our CPU representative vectors, like this: row 1 into column 2, row 2 into column 2, and the third vector would be row 1 into column 2, right? So we allocate memory like this. Then we can also copy memory. Once we've allocated, we cannot copy memory to another another memory location unless we have allocated it. So we allocate some memory on the GPU, then we can copy it from the CPU to the memory, CPU to the GPU, by using this CUDA memory host device. And if you want to copy from the GPU to the CPU, we use something like CUDA copy device to host. So here you can think of the device as the GPU and the host as the CPU. So the host is yeah. Alright, so this is pretty cool, don't you think? So once we have done this, we run this kernel, and this is actually non-blocking, but this is actually waits for kernel to get over, but this is actually non-blocking function. So it just calls this function and goes on along its way. So this is asynchronous, you can think of it. So we send in our like A, B, C, which is our LHS, RHS, and resultant, and we send in some functions like a column 1 and a column 2, just to, we need this information to calculate our sum for the loop, for the third loop. So let's step into this. So what do you think this is? So this is just a template of like the templating. It also works in GPU kernel. So this is called a kernel, and the kernel can be recognized by 3 brackets, 3 brackets like these, and in here you specify the block size and the thread size. So a GPU, the cores of the GPUs are divided into blocks, and generally there are around each block is a collection of 32 threads, okay, generally, or 16 threads or something like that. And I'm not sure, but you can also do something like, you can give so each block, I think, represents a streaming microprocessor, That's what a core is also called in GPUs. And you can run around any number of threads on a core on a streaming microprocessor, but the ideal number is around 16 or 32. So you can run as many blocks as you want, but the threads should definitely be around 32 only. So but in this case we are just giving row 1 column 2, which is like the end points of our first two rows, our first two for loops in our O and cube matrix multiplication. So this specifies that there are row 1 number of blocks and each block has column 2 number of threads. And now if we step into this function, so you always preface a kernel by a global variable, okay, and so you can get what block ID it is there is by using block idx.x, and you can get what thread ID it is by thread idx.x. And simply once we have this, so we simply have our I and j. So this is, you can replace this by I, yeah, so this is actually I, but in our previous loop which was, I'll show this to you. So I and k is effectively x is I and y is k here. So it's the same formula, so don't worry. So we are just running those two for loops on separate cores on the GPU, and that results in really great speed ups also. So as you can see, this works pretty well. So we're just running the third loop inside by the width that we send in through here, and the second is actually our start res, the starting of our resultant matrix. And yeah, this works out well, really well, I'd say. And once we come back this, we copy this back by offset by the start res, which is a starting resultant, and yeah, this works. And so if you want to see what speed ups we get, is like, I can run this for you, and this will give you an idea of how fast we're actually doing stuff. Undefined reference. Okay, something is wrong. GPU CUDA ops. Oh, awesome. I'm sorry. Yes, this should work. Matrix meets speed test. It checks the speed and it checks the correctness. Obviously we are correct, and that means our code is fine. But you see, as you can see, we get a 73 times. It's faster by 73 times. The GPU is faster than the CPU by by a factor of 73. That's pretty great, isn't it? So if we want to, that's just 124. So if we try like a 124 by 124, that's a big matrix. That's effectively how big an image is. So let's check this and let's see what speed up we get. Okay, 82, and let's see how the CPU does, because that'll be exponential to the power of n, right? So this should be really slow, and we should get a much better speed up this time around. Okay, wow, that took a long while. So you can see the speed up is like almost 200 times faster on the GPU. So that's leveraging parallel programming, and we hope to do this even more. And so right now, as you can see, I've turned my matrix and main.cu to main.cpp to a cu. So I actually cannot run just make all, because like it will fail because it has CUDA code. As you can see, there are errors. CUDA free was not declared. So to for the compiler to understand what CUDA is, we need to compile the whole program in using CUDA, which is this command nvcc instead of g plus plus gcc. Okay. But yeah, so earlier we were using earlier in make we were using g++, but that does not work because the g++ compiler has no idea what CUDA code is. So we need to compile by nvcc. It's like g++ for NVIDIA GPUs. And you have to change your files to, like, the ending should be end with .cu, not .cpp. So that's pretty cool. Yeah, what else is there to tell you? Yeah, there's one problem actually. We can also link, we should be technically able to put our CUDA code in separate files and name them .cu, and make our main file a CPP file, and then just link it with NVCC. But I'm having troubles linking separate code, so I just put it in the matrix.h and just compiled and just renamed the main.cu to main.cpp. I'll try to compile and link the CUDA and the .cu and the .cpp file separately, but that's still going to be a problem. Anyway, so this episode we did GPU programming. At least you guys got a taste of it. If you want to look at the code, it's not on the main master branch or the develop branch. It's on the .product backprop branch, because we actually also have implemented the backpropagation for the .product, which is fairly easy. I'll just step it through for you. So what we did was we made a dot operation, pretty simple like everything else, and then we made a .product implementation. So the backward, as you can see, is this, but the forward is pretty straightforward, which is like it just does a .product, then it initializes a new tensor, returns a new tensor, and then the backward is slightly complicated in the sense that density type. Why is this error coming? Where is the love? Where is the love? Declaration is incompatible with. I don't know why this error is coming, because the program does compile, and we have done a .product right now. Right. Anyway, so let's step through the backward propagation of this. So what this is basically doing is, I'm going to show you an example. So imagine x is of shape 2 by 3, okay, and y is equal to shape. This is shape, not the actual values. So 3 by 4. So our resultant matrix would be of shape, yes, you are right, 2 by 4. So the gradient coming in will be of size 2 by 4. So in the dot product, if you do the math yourself, you'll come up with the same exact answer as dx would be. We need when you get to the complex vectorization, you can also do something called as dimension analysis, and then just look at the dimensions and see what operation should be done with to get the derivative, the gradient of x, what operation should be done with y and grad, so that we get the same dimension. So if we have 3 by 4 here and 2 by 4 here, so we know, so it should probably be grad into y transpose, so that would give us 2 2 by 3, right? And let's see if we have the same answer. The grad into y transpose, which would be derivative of x would be 1, there'll be grad dot, and then it's a transpose of y. Yeah, so we made a new function called transpose. It's just it just changes the shape matrix effectively, just doesn't change the underlying vector, it just changes the shape and returns the transpose. Actually it returns a matrix, so nothing much. As you can see, and then does a dot product, and then so the transpose with the second vector would be just a 1 and a 0, because in a dot product always the second y would always be a 2D vector. Alright, so and when we want to calculate for dy, let's try to figure this out. We need 3 by 4 and we have grad and 3 by 4, so we probably go 3 by, we need 3 by 4, so x transpose, right, into grad, that'll be, we'll get a 3 by 4, a shape of 3 and 4, so that does work out. And as you can see, we transpose our so the TRS index is basically a transpose index. It just copies whatever the shape was of the RHS of our LHS matrix in the dot product operation, which is x, and it just copies the same shape until the last two, and it just swaps the last two. Okay. Where is the love? Where is the love? So then it just sends in 1 and 2 through the backward. So let's call it example. Right. So that's covered, and maybe if we want to see some backward does work, and as you can see, we go through this backward, we come into here, and just I don't know why this error is coming, but it shouldn't be. The ID is grabbing out, I think. So that's the changes that have been made. We've added the dot product backward propagation here. As usual, you can check the code in this branch, dot product back prop. What else? So we've made a utils folder, as I showed in the last episode, and we added the transpose operation, and that was done, and the weights, and I've been trying to so right now we have covered our automatic differentiation, we have covered GPU programming, and we've built out functionality for the basic operations like addition, multiplication, division, and dot products. So now we can actually get to code our dense layers, our batch norm layers, and our dropout, all the other stuff, the optimizers, our synchronous, gradient descent, and now we're in a position where we can go and get started on the deep learning stuff, like weight initialization, right? We'll probably use like Clorote or Xavier kind of initialization that's supposed to work great, and we'll code our ReLU activation function, our sigmoid activation function. So right now, if you guys are following, would be a good time to start tracking the project on GitHub. um, so this would be uh, yeah, so the repo is built Tensorflow. I've linked it in the last episode. I'll link the link this time around too. And don't look at the code, just look at the project section, and you can get a nice view of what's been happening. And we've got comments and everything, and you can just look at the issues. So there are like around 12 issues right now, so these are all really basic. And so we have tracking our development of the dense layer, the fully connected layer, the batch norm, the dropout, the optimizer, like Adam, SGT, or RMS prop and all that, activation functions, loss layer, calculating across entropy loss, and our dataset layer. We need a nice API to load our datasets well. Just get our input and target, and iterate over it. uh, so there's one called memory leaks in creating tensor and ops, and this I've kind of fixed, because so a problem right now is, in the sake of having a clean looking API, we are actually returning the we're returning uh, uh, by dereferencing this pointer. So we're creating uh, a new uh, variable with the memory, and this gets really bad. This is really bad practice, because we can't track the real tensors that have been made. So clones are made, and it's really difficult to find out um, where keep track of all the variables we've made, we've allocated, because it's all on the stack, right? So from now on, we're going to be operating on so from now on, we're going to be operating on just using like pointers for our tensors. So if I'll just show you something. So I've created like a file called operations, tensor ops. So there we are actually we're creating functions like add, multiply, divide for two pointers of tensors, and we're going to be using that from now on. And we're going to just use pointers, and then worry because then the back propagation errors go away, and the weird pointer behavior goes away when you overload your operators. So for sanity sake, we're going to take a step away from building a great clean API, which we're obviously going to do. We're going to use functions. So it's slightly a little tough on the brain, but it's a necessary evil right now. Okay, so where were we? I think I put it in tensor tests, and these were overloads. Oh yeah, tensor ops, tensor. So as you can see, I've namespaced it with tensor ops, and then you can see new sigmoid test and the sigmoid pointer test. So now it looks like we're allocating pointers, and then with the use of this beautiful auto keyword, we can just do multiply, and the code looks reasonably okay. Multiply, add, exponent, add, divide, backward, and just operate in pointers only. So that's another step we're taking towards a pointer only approach, and slightly increasing the usability level of this, but at the same time we're going to learn a lot about C++ pointers. So we're going to be using shared pointers, learn how to detect cyclic dependencies, which do occur when you have shared pointers sometimes. So that's what I wanted to show you is this tensor ops namespace. So we have an add, and then you can see there's a forward pointer operation, which effectively is the same thing uh, as a forward operation, but instead of a tensor it returns a pointer to a tensor. So if you go to the implementation, it's literally the same thing, but it's returning this .t3 and not dereferencing it. We're keeping this for sake of backwards compatibility until we find a good fix. So this is still something you can play around with and get right results. Sometimes, like, I got the right result on the sigmoid, but when you delve closer, you see some of the pointers aren't right if you look at the debugger. uh, I have showed this behavior in previous episodes, so if you want to check that out, please do. uh, so yeah, we have this new forward pointer, and we have our, in overloads we have tensor.h, and I think this should be vector.h actually, because this is a vector overload essentially. Let's rename this vector h, and then operation overloads tensor. Yeah, new some variable proper, and this should be okay. Operations types matrix.h. Okay, matrices. Wow, we're taking the whole way through overloads and vector.h, and it's fixed. That is all, I think. So now we're at the steady state, and so we have a GPU code here. We actually, you can see here we have a main.cpp file, not our .cu file. So we don't have the GPU code in this branch. You'll have to go to .product backprop for that. But I built some tests too. So I've refactored the tests from our matrices test, which we saw last time. It's the same thing, just in matrix.h. And then I've created some tests for tensors, just to check if the result is coming fine. And it's the same thing as the matrix multiplication, but then we have this cool test called the computation graph, which basically tests that the pointers are right and the gradients are being calculated correctly. This is effectively gradient checking, but not by using the grade school formula, the high school formula. And then we check the backward propagation. So these are two tests, and it's called, there's a utils function that checks if two matrices are equal, and there's a main function which just runs all the tests and then just calls these two header files of the test, matrix and tensor. So that's about it. Tests, overloads, operations, we have got a dot operation, and a backpropagation for a dot operation. We have a GPU code in short GPU, and a utils. That's about it. So we're pretty stable now, kind of, but we're going to start making layers now. So the next episode we're going to build our fully connected layer, so that will involve I'll show you git commit, yeah, what's it, renamed file. And then, so the latest thing I'm working on is dense layer. So this is, yeah, as you can see, there's a new folder, layers, and a dense layer has, so I'm initializing the weights using something called Xavier Glorot initialization. So if you guys want to read this paper, it's called Understanding the Difficulty of Training Deep Feed-Forward Neural Networks, and this came out in 2010, long time ago. But It's a standard in deep learning now to initialize your weights like this. Then you have a biases, you have weights, you have your input size, your output size, and according to that you initialize your weight matrix and or your biases, and then you forward prop, which is just a dot product, and then you apply your activation functions. In this case it's sigmoid. You should turn this into a ReLU because sigmoid always results in exploding or vanishing gradients in deep networks, so it's not a good activation function. And then we just add the logits and the biases to get our Z, and then we return the Z. And then we just do Z dot backward, and it will automatically happen, because that's the beauty of automatic differentiation, modular automatic differentiation. Alright guys, hope you liked this episode. Just more of like no coding as such, just showing you how we built it and encouraging you to look at the code. I think the future lessons will kind of be like this, because it is difficult for me to code in front of you because I make a lot of mistakes. So generally the next episodes will be, I'll be walking you through the creation of the dense layer, and maybe we'll code it out. Please let me know in the comments if you'd like me to code in real time. Alright, have a nice one guys, see you next time.